Just wanted to make one last video for you guys while I'm gone. This is called percent yield. The percent yield is actually a pretty simple calculation. The percent yield, when we say the word percent yield, basically what we're talking about, imagine you do a lab and you take so much reactant, you react it together with some other kind of reactant, you form a product. If you know how much you start out with in a chemical reaction, through the use of BCA tables and the problems that we've been doing, you should be able to accurately predict how much product you are actually forming. And so what this percent yield allows us to do is it indicates how well our lab data, in other words, how well does the mass of the product that I actually obtained in the lab compared to what the theory says that I should have gotten. And so this is what we call the percent yield. It's just calculated by actual over theoretical times 100. And when I say actual, what I mean by actual is lab value, so what I obtained in the lab. The theoretical value is the value that theory says is right. In other words, through the use of my BCA table and stoichiometry, how much product am I actually predicting that I'll form? So I want to give you an example of how we can use this percent yield by looking at the previous problem here. So I've got a problem much like what we had in the previous videos. I've got 5 grams of aluminum react with an excess of hydrochloric acid. It says to determine the theoretical yield in grams of hydrogen. What is the percent? Then it says, what is the percent yield if 0.525 grams of hydrogen actually formed? Now, this is where most people get confused on these problems. Do not. Notice that it says determine the theoretical yield in grams of hydrogen. Stop. Ignore that statement even exists. You got to answer the question before that first. And so I'm just going to completely ignore that guy. Act like it doesn't even exist. You first need to determine the theoretical yield in grams of hydrogen. And so down here, I'm going to come down here and look, there's my chemical reaction. The first thing I need to do is to balance it. Well, to balance this, I've got a 3. I could put a 3 there, but I've got a 2 of the hydrogen, so that's going to make things wonky. The least common multiple between 3 and 2 is 6, and so therefore I'm going to make that 6. And that would mean you need 2 of those to balance out your chlorines, and then you need 3 of those guys, and then you need 2 aluminums over there, and that guy should be balanced. Let me keep making room here. Voila, balanced. So now, I look back up at the problem, ignoring that third sentence there because I don't want to deal with that right now. I'm trying to determine the theoretical yield. In other words, I'm trying to determine the amount of grams of hydrogen. So I ultimately want to know this guy down here. I want to know how much hydrogen gas I'm forming. Well, I know something before I even start on every single one of these BCA tables, and that is 0, and I've got 0 over here because those are my products. Well, now let's look over here. 5 grams of aluminum. Oh, 5 grams, that's telling me the amount of aluminum. I can put 5 grams right there, right? Wrong. The reason you cannot do that is because grams does not go in a BCA table. Grams indicates the mass of the aluminum. I need to have an indication of the number of particles, which is in moles. And so for aluminum, what I would do to figure out the number of moles in 5 grams of aluminum, I would say, what's the molar mass? Well, I look it up on the periodic table. It has a molar mass of 27 grams per mole. So therefore, I would set up a basic ratio. 27 over 1 mole, because that's how many, if I have 1 mole, I'm going to have 27 grams of aluminum. Well then, if I set that, I'm going to do things a little bit differently here, I think. Oh yeah, I'm going to like this. Equals, and then I can set up my proportion. Imagine there's a division sign right there. Well, according to this problem, I'm given 5 grams. 5 grams would then go on top. On bottom, I would call that X. And so then, how do I solve for that, assuming that this is a nice division proportional reasoning right there? Oh yeah, it's money right there. Well, the way you do that is you'd say, okay, I've got to take 27x 27 times x is equal to 5. So then to solve for x, you divide both sides by 27. So you take 5 divided by 27, and you're going to get x being equal to 0.185 moles. Now, that is how many moles of aluminum are present up here. Now, usually I always write units, but I'm going to run out of room, so I'm just going to write 0.185. And if I assume that all of those change, I'll go minus 0.185. Now I could take time to fill in the rest of these, but really I don't really care about it because all I care about is the amount of hydrogen. So what is my ratio from once I got one thing on the change row, I can then make my comparison. And so I want to compare the amount of aluminum to the amount of hydrogen on the change. And so therefore, what's my ratio? Well, that's a 2 to 3 ratio. That's not in my head, so I'll just come down here and make that ratio real quick. I'll say 2 aluminums, because that's what was in the balanced chemical reaction, over 3 hydrogens. Hydrogens like so. That is going to be equal to, and again, imagine there's a division sign there. Well, in this problem, I just figured out that I'm losing 0.185 moles. Well, how many moles of hydrogen are there? Well, gosh, I don't know. I call that x. Little x, I guess. And here's my proportion. Over. Now, how do I solve for that? Well, you cross multiply. 2x, because 2 times x is 2x, is equal to 0.185 times 3. That is, according to my calculator, 0.555. Well, then how do I solve for x? Well, then I divide both sides by 2. So I divide by 2. That is equal to 0.2775 moles. That's how many moles there are. So then again, I come up here, I'm starting with 0. Oh my goodness, this is coming together real nicely. Plus 0.2775. Therefore, my product will be, my number of moles is 0.2775 moles, just like that. So that's my answer, right? No, not so fast, because it wants it in grams, not moles. And so again, I'm going to have to figure out the molar mass of hydrogen. Oh, well, this one's easy, because the molar mass of hydrogen, I look about on the periodic table, each hydrogen has a molar mass of 1 gram per mole. Well, if I'm dealing with H, not just regular hydrogen, you're dealing with H2, then I just simply double that. The molar mass is 2 grams per mole. And so again, I can set this up. I would say 2 grams over 1 mole is equal to, and I just found out that the number of moles that I have is 0.2775, so I would put that on bottom because that's where moles are, 0.2775 moles. Call the top x. Then I again cross multiply and divide, and so then I would have x is equal to, and all I have to do is take 2 times that, 2.2775, so I have to multiply it by 2. What do you know? You get 0.555 grams. So that right there is your answer to the theoretical yield, or the amount of grams of hydrogen that's produced, is 0.55. Now I can read this next question. Well, according to my BCA table, I just figured out my theoretical yield of hydrogen was 0.55 grams. 0.555. Then it says, what is the percent yield of 0.525 grams of hydrogen if it was actually formed? And so that's saying in the lab, you actually formed 0.525 grams of hydrogen. Well, according to my equation right here, man, I've got this. Watch. All I got to do is say my actual. What did I actually form in the lab? Well, that, according to the problem, is 0.525 grams. Well, what did theoretical, based on what I just calculated in theory, what did that say it should be? Oh, well, that was 0.555. And so all I have to do to calculate my percent yield is take my actual, which is 0.525, divided by 0.555, hit equal, and then to make it a percentage, I just need to multiply it by 100 times 100, and that then is 95%. And so therefore, you have a 95% yield, which basically means that your actual value came out very closely to what you should have gotten in the lab.